Hello, ladies and gentlemen. In this talk, I would like to report about how the interoperability technologies Automation ML, OPC UA, and Asset Administration Shell fit together. This question raises confusion in industry, and that's why I invited the Automation ML Association, the VDMA, the OPC Foundation, and the IDTA to jointly cooperate and to find a solution and to define a big picture how they should work together. Who's talking to you? My name is Drath. I'm a professor of mechatronic systems engineering at the Fordham University. I'm a board member of the Automation ML Association. I'm the architect of Automation ML and advisory board member in the GMA. I'm a teacher, book author, an inventor, and a consultant. And what is interoperability at all? It is the capability of hardware and software to communicate with each other in a meaningful way. It should be enabled cross-vendor, cross-platform, and cross-domain, even with unknown partners. We all know that this requires harmonized data models, and this again means standardized syntax and semantics, or at least known semantics. But many people don't know that this requires complex iteration functionality. I show you why. To understand the need of complex iteration functionality, I start with a prediction about the future engineering of our future plans. In future, we will distribute our world into the cyber world of data and services and a physical world of real objects. And the first step will be the modeling of requirement models. Instead of just writing down our requirements, we will model them explicitly in electronic and digital data models that are machine readable. And here we collect everything we need, all the objects and the features we want. And then we upload it into the cloud. So here we have an upload functionality into the cloud. So we have a first use case for complex object models. Second, vendors will provide their product catalogs no more just as PDF or as website or as a printed catalog. They will provide their product catalogs in an electronic and digital way, in form of digital data models that are machine readable and can be retrieved automatically. And because in the first step I have defined electronically what I want, in the second step vendors provide me what the products can deliver, the device selection can be automated at least to a certain degree. In the third step then I do my selection and I create instances of the different products that I need, a valve, a motor, a robot, whatever I need. And then I create my instance model, it's a plant topology, and this is quite complex. Every object still remembers the requirements, it still remembers the assurances from the product vendors, and it adds the instance relevant information like an IP address, for instance, or the inventory number. Here I can generate documents, I can do simulations, optimizations, and so on. So, and once I'm done with this detail engineering, I'm going to order my assets. They are then submitted to site. And then I do the automatic generation of the information model of the plant, the runtime model, and my instance model of the engineering and the information model of the plant, they are well interconnected. Meaning I can, for instance, bring the simulation model in the instance model into the situation of my current plant. I can retrieve all the process data to do modifications, tests, simulations, and to find errors. And they are well interconnected. And in the last step, we do the iterations, meaning we do not engineer our plans in one step, but we do then modifications over time. So you see different points of object models, of interactions of object models. They are uploaded here, they are downloaded here, they are created here. In the third step, of course, the instance models need to be shared with all participants. And then we have information models on the plant side. Lots of object models that need to be shared and submitted forth and back. And that's why object models are very important. To make this vision come true, we need to be able to model complex object models. And on the left-hand side, you see an Automation ML model, just of one cable. The cable comprises a plug and a socket and a wiring, and all the interconnections between the pins and the wires are present. You see just one cable is quite complex already. And then when you go to a fair and ask for data exchange, what they show you is this. They show you, hey, we have an engineering tool here, you do the data export and store it in a file, and then you import it into the receiver's engineering tool, and then you are done. But this is unfortunately too simplified. In reality, it looks more like this. In the first step, the data receiver has to request data, and the data sender has to explore the data to find what the data receivers want. And then he has to do a data selection. And before he can submit the data, he has to do difference calculation to find out what has changed since last time. This is data management. And then the data sender is doing the data export. And then the receiver has to receive the data, and before he can import them, he has to analyze them. He has to find out the differences according to the last version and according to what's inside the current database. And then he has to do quality control to find are the data proper, are they correct, do they match with my expectations. Then there might be a feedback loop if there are complaints, and there must be some feedback step here where the data sender can explain why he has changed this, or he can make corrections and can incorporate the feedback back into his engineering tool. And both parties continue engineering over time. So it's really a complex thing, and for all of these things you mostly don't see any presentations on the fair because Excel cannot provide this. And now we have 3 different interoperability technologies on board: Automation ML with their Automation ML domain libraries, the Asset Administration Shell with their AAS submodels, and OPC UA with its OPC UA companion specifications. Scientifically, they look very similar. They all do object-oriented modeling in a structured way. They create libraries and they create templates, and they do semantic and syntactic modeling in a machine-readable way. And the question is now, why do we need 3 of them when they are so similar? And so I'm asked in interviews, has OPC UA overtaken Automation ML? Is the AAS overtaking OPC UA? Is AML and OPC UA equivalent? We only need one. Are AAS models just data providers with online access and can do everything, and Automation ML and OPC UA is legacy? Yeah? And I read in scientific papers that one of the biggest challenges in industry is that companies have to convert all their data models into the Asset Administration Shell meta model. And the AAS can export data to AML, JSON or OPC because it's a good idea that industry can select what they want. And for engineering, the AAS solves all consistency issues in a heterogeneous tool landscape. And by the way, the AAS can do everything: control evolve, can negotiate, perform machine-to-machine communication, and can contract with other AAS. And it achieves incredible flexibility. And it's a start of all interoperability at all. And it is the only digital twin. Have you heard one of these messages? They are all wrong. Please don't be confused by these statements. They are wrong, and I want to clarify how it should work together. And because clarification is needed, I invited the Automation ML Association, the IDTA, the OPC Foundation and the VDMA to discuss and to develop a big picture interoperability and how all these technologies fit together. And it's all written down in a discussion paper. It's not yet final. I'm going to present you the current state of the discussion. The first thing to investigate is just to look into the life cycle. Yes, they are object-oriented models, and yes, these technologies support type and instances. They are very similar, but they are executed in different domains. Let's look into the phases. This is the home of Automation ML. Automation ML is an object-oriented modeling language for data exchange in engineering. It's used by the MTP, it's used by the SCT, it's used by the OPC UA FX, and we currently discuss the application in DXP, and then there are other than Automation ML data formats, device descriptions and so on. So this does not mean Automation ML is the center of the world, but Automation ML is somehow located here and it's used. OPC UA, however, is executed in operation. This is the origin and the home of OPC UA, and it uses object-oriented type models, and OPC UA servers are often generated automatically out of engineering information. So there is no competition at all. They just complement each other. OPC UA is further used in maintenance. And now, where's the Asset Administration Shell? The Administration Shell is somehow in the cloud. It means that the Asset Administration Shell is providing product information from the vendors to be used in the tender phase, in the engineering phase, in operation and in maintenance, but it has no connection to operational data, and it does not solve the problem of the iterative engineering functionality that I explained in the previous slides. Meaning, the focus and the use case of the Asset Administration Shell is valuable and useful. It's all about lifecycle interoperability. And the use case of automation ML is engineering interoperability. And the key use case of OPC UA is operational interoperability. That's the first indicator why these technologies do not compete, but they have their own home of their application. So this means automation ML from its core, it's a tool-to-tool exchange thing. It's specialized for the engineering phase. And OPC UA is an asset-to-software exchange technology specialized for sensitive production data. And the asset administration shell is a software-to-software technology. It's useful for all phases of a plant and used across the life cycle of an asset and has its focus on data that is relevant across the life cycle of an asset. So they form a food chain. They do not compete. They can augment each other in a meaningful way. So that's why they do not compete. They form a value chain. So let's come back into the future prediction of the future engineering. Where these technologies are then located, this is the home of automation ML. Here we have the requirements models, the type models and the instance models. Then we have the asset administration shell. That can be the place where we do the upload and the download from. This is a place where the vendors provide their product catalogs. And this is a place where we submit our requirements models to. And OPC is located classically here directly as an information model of the plant. It's located here down in the field, and it is also located here for the interconnection into the cloud. So, and this is the first step to understand the big picture that the four associations have developed so far. What you see here is in the middle the asset administration shell, the number one. It's a piece of software that intercommunicates between an asset and the phases and their tools in the asset lifecycle. This piece of software acts like a piece of brain that can make stupid devices smart devices. It has a north port here, which is indicated with number 2. This is the interface to the AS, providing an API. Current state is it's a REST API, so that all the tools can access and can find the asset administration shell in the network. And it has a south port that interconnects the asset administration shell with the asset, and this is technology open. There is no technology proposed by the IDTA. So that's the first part to understand the position of the asset administration shell. Now we zoom into the asset administration shell and its internal data household. Look here. It has submodels on board. The submodels are like files that store different data of different aspects of the asset. And the new architectural element here is that we differentiate between submodels and detail models. Submodels are for the models of cross life cycle interesting information, and the detail models might be automation ML files, geometry files, simulation files, even binary large files, for instance in TIA Portal project, that is just referenced from the submodel to provide details. And this separation has two benefits. First, we don't need to remodel detail model information in the submodel. And second, we can distribute the detail models independent of the asset administration shell framework, because there are many use cases where we don't need the industry 4 ecosystem. Next step, we move into the production side where the asset is. Here you see the asset administration shell has no connection to. This is the home of OPC UA, and by the way, many other interoperability technologies like field buses. But if we look on the position of OPC UA, it's here. And here we have the companion specification, lots of companion specifications and interconnections between devices and to the gateways and up to the clouds. This picture shows the overall big picture interoperability and where OPC UA, the asset administration shell, and automation ML are located in harmony. So they do not compete anymore, or they cannot even compete. They augment and complement each other. While the asset administration shell with their submodels provide product information, the detail models provide all the vast amount of engineering details, and the OPC UA information models are dedicated to the production and to the sensitive operational data. And of course, there's a bypass here that allows proprietary tools to have a direct connection to their proprietary assets, for instance, for download, parameterization, and whatever purposes. Especially in the cooperation between Automation ML and the Asset Administration Shell, this picture seems to be important for me. We have a strict data separation between the submodels for lifecycle relevant information and the detail models, for instance an MTP file that is just referenced and that contains lots of information that you do not want to model in a submodel. As part of the work of the 4 different associations, we have formulated 10 different application recommendations how to use Automation ML, how to use OPC UA, and how to use the Asset Administration Shell. And the first rule is please avoid uncontrolled growth of submodels. Yeah? We recommend an accessible, transparent and regulated development and certification process in the different organizations and associations to just avoid uncontrolled growth of submodels. Second, we propose to prefer referencing instead of remodeling. Existing formats and information models such as Automation ML, the OPC UA companion specifications and the AAS submodels should be referenced but not modeled again. Number 3 is we propose a targeted and economical data management. The AAS submodels should only contain essential and life-spanning information. This really simplifies the standardization of submodels. And the AAS submodels should not be overloaded with details. Every little property requires a short and conscious use case to prove the need, its existence in the AAS submodels. Some people believe submodels should contain everything because we might use it in future, but please consider that standardization is a long time effort, and that's why please focus first on what you really need. Number 4, we say that detailed technology-related information should be stored in the established data formats. The AAS should not be misused as a database, but should reference the detail models. Number 5, we believe that the AAS should run independently of its asset in the connected world, or in the cloud, or in the edge, but not on the product field device. Do not run the Asset Administration Shell of a robot inside of a robot, because if the robot would be down, the Asset Administration Shell would also be down. Then we propose use the Asset Administration Shell for the exchange of cross-lifecycle product information. Use OPC UA for the modeling and exchange of operational data. And use Automation ML for storage and exchange of object-oriented engineering data. Number 9, here we propose that AAS software development kits should provide mechanisms that allow easy and direct access from the AAS deeply down into detail models. Meaning an AAS should be able to natively read an Automation ML file and to give access to the object model from its nature. Just to avoid that companies need to read the models, the detail models by themselves. This facilitates direct access to reference content of the detail models. And number 10 means avoid competency conflicts. The data should be defined and standardized by subject matter experts in the domain where the data originally occur and or have already been defined. Do not reinvent the wheel. Not the quickest should win, but the ones who have the competency about this domain. So in summary, we believe that the interoperability between Automation ML, Asset Administration Shell and OPC UA works seamlessly if we follow basic rules. The discussion paper is available here on the websites of all of the 4 organizations. This is just an example from the Automation ML website. We think Automation ML, OPC UA and the Asset Administration Shell do not compete. The organizations behind these interoperability technologies host the experts and expertise in their individual domains. The approach integrates years of mature knowledge and expertise. They all have useful points of contact, and we believe interoperability is not achieved by a single world model, but by a clever combination of different standards. Thanks a lot for your attention. Have a nice day.